Okay, and I show both ways in the Excel and they match. So this approximation work for depth is longer than half of the diameter. So you have to vary it, not like partially above the ground or something. And when you actually do it, you don't do partially above the ground to begin with, right? Okay. The one thing that you need to know is ksoil. How much is the thermal conductivity of soil? Do you believe that people try to find that value like crazy? See this? Dry, peat, wet, icy, dry, moist, soap, dry, moist, wet, frozen, sand, gravel, limestone, sandstone, everything. Okay, they find every value. So there's a range. So this is like 0.17, 0.5, 1, about 2. So this is the range of thermal conductivity of soil. So if it is not given, you have to guess which value that is reasonable for you. So you just pick one. Okay, if you have a sand soil and it looks dry, it's not that wet, so you use this range. If it's wet, use that range. Okay? What about if you are in Gulf of Mexico and you bury the pipe under subsea? What is the soil thermal conductivity? So you find some information from literature. So this is a plot, another plot for the moisture content versus thermal conductivity of soil. So it depends on how much is the moisture content. You don't know, right? You cannot like just take soil on the subsea. So you just, if you want to be conservative, you use highest value. Okay, that will give you conservative approximation. Where's the sign-up sheet? Can I have it, please? Everyone sign it? Who haven't signed it yet? Marshall, can you count the number of signatures, the number of students in here, please? Did you count? Okay, find out. Oh, only one person. So you have 61 here. Let's count. So this is the thermal conductivity of soil in Gulf of Mexico. Okay. Put everything together, you have that term and that term. The reason that we have just these two is because the vary term and the insulation term is a lot higher than that Nusselt number thing. Okay? 1 over HIRI and 1 over HOR is quite small. So this is calculation example that Excel file is already posted. Your job is to read it, okay, and find out what did I do. And this give you, okay, let's go over this a little bit. So I have 2-inch schedule 80 carbon steel pipe, flow rate 1,000 barrels per day, oil density 800, inlet temperature 150, oil viscosity 5 centipoint, thermal conductivity is 0.13. This is a typical value of crude oil thermal conductivity, and I use 2000. This is a typical value of crude oil heat capacity. Pipe length 4 miles. Pipe not buried, no insulation, just above ground. Okay. Wind speed 20 miles per hour. Ambient temperature 35 F. Air property, I Google it and use engineering toolbox to find the air property for density, viscosity, and Prandtl number. So with Prandtl number and viscosity and Cp, you can calculate the thermal conductivity, right? Thermal conductivity of carbon steel pipe is about 50 or 54 watt per meter per Kelvin. One of the assumptions that I have to make is fluid property is the same everywhere. It's not a function of temperature and pressure. And we have only single phase flow, no gas coming out. That's the assumption, okay? And I cannot find exact match, and I didn't do the linear integration, so I use the property at 35.55 for the condition of 35. So ambient temperature is 35 Fahrenheit, but I didn't find the fluid property at 35. What happens when you do this is you get error, quite a quite a little bit, depending on how much your temperature change. Why do I say that thing? So when fluid property change with temperature, what do you think happened? Who want to help me? No one. Kai. Okay, next to you. What is his name? Pen. Oh, Pen. What do you think happened if the fluid property is not constant? If it changes with temperature, what do you think happened? Let's take a look at the temperature profile. Temperature profile, we get something like this, right? No insulation, not right. You get that. So, what happened to oil viscosity when temperature go down? Increases linearly or exponentially? Or a little bit? A little bit? A lot? A little bit or a lot? So when your temperature drop from 150 to about 35, it go up a lot. So viscosity go up actually exponentially when the temperature drop. So density rho is not quite sensitive to temperature. It has some effect, but not that much. The term that have a lot of impact on the fluid property, the temperature have a lot of impact on viscosity. Viscosity go up exponentially, okay, when temperature drop. So when I assume one viscosity everywhere, that's giving error, okay? It's not accurate. But let's do that thing first. So first step, I get Q, variable there. I convert it to cubic meter per second. I calculate flow area, pi d squared over 4. I calculate velocity, about 1 meter per second. I get the pipe roughness. I say, okay, if I use carbon steel, open the website, pipe roughness is about 45 micron. So I get epsilon over D, pipe roughness over inner diameter. So that is for friction factor, right? I calculate Reynolds number is 7,600 something. So that's turbulent flow, more than 4,000 turbulent flow. Good? That's turbulent flow. Then I don't use the explicit form. I use the implicit. I use the explicit form, not the full Coburg equation. So I use Haaland Equation to calculate fanning friction factor. That F is fanning. So this is the equation given for you. Calculate frictional pressure loss. Have you seen this before? Something like this, right? So without reading the chart, put all the number in. Pipe roughness is over there. Put everything in. I get friction factor 0.0085. Okay. Then I have frictional pressure loss minus dPdL equal to 2F rho V squared over D. That is for fanning. If we have closed book exam, this equation is not given. I want you to memorize it, please. Okay, good. Landon, you like that? You like to memorize this? Memorize it. Memorize, and I tell you today, and I probably tell you more later. You will memorize it. At least memorize for the next quiz or something. Good? Memorize this. 2F rho V squared over D is equal to minus dPdL. Frictional pressure loss per unit length. Can you memorize this, Victor? Easy, right? Go back home. Spell it out. Pronounce it 10 times, 20 times. Okay, memorize it. I get 60 psi per mile. 60.6 psi per mile. So that's my frictional pressure loss. This doesn't have anything to do with the calculation yet. Okay. I go back. I calculate Prandtl number of oil. Prandtl number of oil. Then I use Reynolds number. Prandtl number of oil. Put in detachable alter. I get Nusselt number. I don't worry about that term. Okay. I do the same thing for Kanedinsky equation. So I get Nusselt number about 100 something. And Kanedinsky give me Nusselt number about 100 something. This number is something that you want to know, okay? Because if you get something like 10,000, it's not a typical value, it's wrong. If you get something like 10,000, So you should get something less than 1,000, okay, for Nusselt number, especially for flow in the pipe. So it should be about 500 or between 100 and 500 if you have turbulent flow. For laminar flow, fully developed, you get about 3 to 4, not 100 or something. Okay, laminar flow has a lot less Nusselt number compared to this. After I get Nusselt number, so I get HI, right? Then I calculate the one outside. Thermal conductivity, get from Prandtl number definition, and I get the Reynolds number of air outside. So that's the density, velocity of air outside, convert from 20 miles per hour to meter per second, put everything in, get Nusselt number for air, that much, 122. Nusselt number for air. I know the definition of Nusselt number is HD over K. So H is Nusselt number times K over D. Nu equal to HD over K. You know that, right? Okay. So I get HO. HI NU K over D. So I get HI. Okay. And 1 over HIRI, just 0.1. Not a lot, right? And this one give me 0.6 something. I calculate heat resistance from the pipe, natural log of outer radius over inner radius, but I use OD and ID. It's okay to use ratio of OD and ID because ratio of diameter is the same as ratio of radius. Okay, over K pipe, I get the number. I calculate overall heat transfer, I call it overall specific thermal resistivity. Okay, specific thermal resistivity. So each term add together, so I have 0.78. Okay, 0.78. I calculate m dot, mass flow rate in kilogram per second. That's 1.4 kilogram per second. U times R, that's what I want to get, right? So U times R is just the inverse of 0.07. This means the exponent excluding z is 2 pi r u over m dot cp, has minus sign. So I put everything together, I get this form. I substitute back to the original equation, I get T in Fahrenheit equal to some coefficient multiplied by that, and z is over there, and 35. Done. Easy, easy. Plot it, I get this line. Good. And exercise already given. If I know that you do the presentation this Saturday, you may not be able to do it on time, but next time when you do the presentation, hopefully you can find some good from this thing, okay? So example 2, for the case that bury the pipe. For the case that bury the pipe, I told you earlier that HO is not going to be valid, right? Because HO is a flow around the cylinder. But if, so flow around the cylinder, that's HO. The equation that has C and M, you remember that? This equation. If you bury the pipe, you don't want to worry about that much because the value is small. So when you bury the pipe, have one more term. And that one more term is arc hyperbolic cosine. In Excel, you put ACOSH, okay? Get the value. Or if you want to check with another formula is that formula. You get the value. They are identical, okay? Same. So this gives you 1 over H soil R soil. Put it back. So it's one more term pop up in the overall heat transfer coefficient, right? You calculate that, then update the exponent, then you can plot the graph. Okay. Example 3, insulate and bury. So this term is for bury, and you have one more term for insulation. When you have insulation, you know that the log go from outer radius of that layer divided by inner radius of that layer, and everything divided by thermal conductivity of that layer. Put that term in. Done. So I get 25. So I do another one without bury the pipe, just have the insulation, what happened. So I do this, okay? And then plot it, get several lines. So you see if you have 4 miles, temperature will drop, right? What you will do in the homework is you will try to change flow rate. What do you think happened to the temperature profile if you increase the flow rate? So let's say you have the bare pipe. You make it flow faster. Will you have this line or will it drop faster like that? You go do your homework, okay, and you tell me in the homework. I will grade it. If you flow faster, probably you have less temperature drop. Think about it. If you can move oil instantaneously from wellhead to your target, you don't have enough time for any temperature to drop. You just get there instantly. So if you travel very quick, you have that, right? If you travel a little bit slow, so it has some time for temperature to drop. Okay? Alright. There is a better way to do this. This time we assume everything has the same viscosity. Viscosity and density is the same everywhere, right? That's the assumption. You can do better by discretize it into small sections. So let's say you discretize it into 100 sections. So you have section 1, section 2, section 3, section 4, section 5. So, and so on. You have 100 sections. You use that technique for just first section. You have temperature drop in the first section. AJ, that's good, right?
Temperature drop in the first section.
That's good. You can do it, right? Okay. So when you get the temperature drop in the first section, you use that and you get pressure drop too, right? You use that temperature and pressure to update the fluid property that you are going to use in the second section. Let's say your temperature drop by 3 Fahrenheit and your viscosity go up by 2 centipoint. So you update the fluid property and then you calculate again. Once you get the temperature and pressure at the end of section 2, you update the fluid property, you calculate again. You do that. So your graph will, in each section, it will be calculated based on different fluid property. This is better, but still not that good, not as good as you can do. You can do better, right? Think about it. If you have your temperature profile look like this, right? But viscosity that you use in the calculation. So on the first section, you use inlet temperature to calculate viscosity, right? So that is the temperature that you use to calculate viscosity. Once you get the temperature at the outlet of first section, you use that temperature to do the calculation of second section. So you assume that your fluid property is the same everywhere in that section. So you have something like this in your calculation. That's what happened. So if you want to do even better, you use implicit approach. Okay, you get temperature and pressure at the next point, calculate the average, and then use the average value to do calculation. Oh, okay, I have 4 more minutes. We can talk about it. So implicit approach, of course, this is not in the exam or quiz. The explicit one, this can be in the exam or quiz. Okay, so you just separate it into several sections and then you do calculation. This requires we to have a function of fluid property and temperature and pressure. Okay, so this means at first you need to know what is viscosity as a function of temperature and pressure everywhere, or density as a function of temperature and pressure. Okay. So second approach, which is implicit, require a little bit of iteration. So this means you use explicit, you discretize it into many sections. Then use a explicit approach to calculate the temperature profile. You get this line, right? So you know the temperature that you calculate. That temperature is based on the fluid property defined at the inlet, not the fluid property at that point. Not good, right? So there's some discrepancy between fluid property that you use and actual fluid property because it changes with temperature. So then what you do is you use explicit method to get the temperature at that point. Once you get the temperature at that point, you don't accept it as a final answer. You know the inlet temperature, you do linear interpolation, so you average it. So you know the fluid property at the middle, and you know the temperature at the middle, right? And use the temperature at the middle as the representative temperature to calculate fluid property. So let's say temperature at the middle is 149. So you use 149 to calculate fluid property. Then you redo the calculation again. Use new fluid property. You get the answer at the end. Okay? So you have middle and initial point. Average it again. So to get average temperature, use average temperature to calculate the fluid property at the middle. Use fluid property at the middle to calculate the profile again. Then you will get the new point. After the third iteration, you get the new point. Use the new point and the first point to get the temperature at the middle. Just average them. And use the temperature at the middle to calculate the fluid property and use that fluid property to calculate the profile. You keep doing this until that output doesn't change, until it's converted. Okay? Then you move on to the next section. Next section. So this means you use the temperature at the middle or fluid property at the middle to calculate the profile in that section. Okay? It's still not the best. If you want to do better, you can solve dTdz, dPdz simultaneously, use some numerical method. Okay? That's not covered in this class. We do credit school. Oh, it's 12:20. We are 30 seconds left. Okay. Goodbye. See you next time. Do homework. Okay.